Right, in part 1C, you need to find what volume of base gives you a certain pH, pH of 4.745. Now, initially this might seem to be a little bit hard to figure out, but when we look at our relationships, what we know, for example, we are somewhere along this curve. We are either in the buffering zone, or maybe we get all the way to the equivalence point. Well, a little bit of reading ahead says D wants to know what is the pH at the equivalence point. So it's virtually impossible to imagine that they would ask you the same question 2 times in a row. So this is not the equivalence point. It's got to be somewhere before. We've already done one where we were just somewhere between equivalence and the origin. So just being a smart test taker, this makes me think that maybe I'm hitting my other sweet spot, the halfway to the equivalence point. But how could I check? I could check by putting it into the HH equation. pH equals pKa plus the log of my concentrations, right? And I know that I'm looking for this pH, 4.745, and that would equal pKa, which is the negative log of the Ka, which is 1.8 times 10 to the minus 5, plus the log of concentration of A minus over concentration of HA. So, what does this equal? 4.745 equals 4.745 plus the log of my concentrations. Clearly, these are the same. pH equals pKa, which means this has to be 0. The only way this is 0 is if this concentration of A over the concentration of HA is 1. So that means they have to be the same. That's what we said happened when we are halfway to pKa. These are the same. Just remind you, that's true because the way this behaves, HA splitting up into H plus A minus, is that when 1/2 of this has been reacted away, it has produced the same amount of A minus. All of these H pluses are being neutralized, so they're turning into waters. But essentially, if I start with 10 of these, if I react away 5 of them, I make 5 of these. So I've got 5 of each. If I start with 100 and I react away 50 of them, I've got 50 left behind and I've made 50 of these. So the two numbers are the same. This term equals 1, pH equals pKa. So okay, great. Now what do I do? Well, since I can see that I must be at 1/2, I know from the first problem that my moles of HA was 0.1125. So I am halfway from that to 0. So divide this by 2 at the volume where I have 0.05625 moles of HA. That's when I also have 0.05625 moles of A minus, and I get there by adding 0.05625 moles of OH. So I'm saying that when I get to the point where these two numbers are the same, I have added OH enough to get this many moles from my original gone. Halfway there. So, what volume of 0.800 molar NaOH has that many moles in it? 0.05625 moles in it. This is moles per liter. This is moles. I need to find liters. So, even though this is not included as one of your equations, we know that since molarity equals moles per liter, if I want to find liters, liters must equal moles divided by molarity. So, what volume do I need? I need 0.05625 divided by 0.800 moles per liter. So that means I need 0.0703 liters, or 70.3 milliliters. As long as you have the unit, either one is fine. So that's the answer. What volume of base will give me this pH? That pH is the pH when you have pH equals pKa. When pH equals pKa, the two concentrations have to be identical, and I get them to be identical when I have made 1/2 of these get neutralized, leaving behind the same amount of A- as H+. So I just took my original moles of HA, divided it by 2. That's how many I have to have left, which is how many OHs I have to add. And to get that many OHs, I have to put in 0.0703 liters.